Welcome to All Space Considered. What you're currently listening to is the sonification of space images. The light is translated into sounds. I'll tell you more about this during tonight's show, which will start in just a few moments.
Ladies and gentlemen, welcome to tonight's All Space Considered. Tonight's program is pre-recorded, unlike all our other All Space Considereds, which we bring to you live, which we will do again next month. We'll come to you live, so be ready for that. But we do hope you enjoy tonight's pre-recorded program. It is brought to you by the City of Los Angeles, the Department of Recreation and Parks, Griffith Observatory, and of course, our nonprofit partner, the Griffith Observatory Foundation. And we appreciate all that support. Tonight's show with me, as always, is Patrick So and Chris Butler. We've got a great program for you. Everything from Bill's secret sonification topic to an update on Perseverance and what's been going on there to Out to Launch with Chris Butler. And of course, as always, we'll have a Sky Report. Now, tonight, we also have a very special guest, University of Surrey's Dr. Michelle Collins, who's going to talk to us about a paper that's been 7 years in the making. It's about dark matter in Andromeda 21, so make sure you stay for that. Hope you enjoyed tonight's show, but first, Bill, what is that sonification you were telling us all about?
The beautiful images you saw pre-show were sonified. The light was translated into sound. This allows us to hear the objects as well as see them as the bar sweeps across each image, either bottom to top or in a spiral motion like the second hand of a clock. This is also a way for people who are visually impaired to experience the beauty of space. In the case of light that's not visible, not in the visible part of the electromagnetic spectrum, such as X-rays, that's all of us. Much of what we will see here has already been translated into colors that are visible to us. How were these images converted into sounds? Well, different techniques were used. Brightness controlled volume. The brighter the light, the louder the sound. In the Chandra Deep Field image, where the horizontal line sweeps from bottom to top, the longer wavelength light, that's the red end of the spectrum, was assigned to long wavelength sound, which means lower notes. Light toward the violet end of the spectrum is shorter wavelengths, and shorter wavelength sounds are higher pitches. Dots toward the left side of the channel, and those were placed into the left stereo channel, and those on the right side of the picture were placed into the right stereo channel. And by the way, the pretty dots in that image are mostly not stars. They are almost all distant galaxies. The cat's eye is a planetary nebula. Our own sun will likely become a planetary nebula someday, about 5 billion years from now, so mark your calendars. And light closer to the center of the image was assigned to lower pitches, and light farther out became higher notes. And all the notes come from a major scale. The Whirlpool galaxy is a spiral galaxy like our own, the Milky Way. It's imaged in a range of wavelengths: infrared, optical, ultraviolet, and X-ray. Each of those ranges of light was assigned a different sound range. The sounds are based on specific pitches in a melodic minor scale. This one uses the sound of a choir, a harp, and a piano. Remember, we will run this whole remarkable video at the end of the show this evening. Thanks.
Well, thank you for that fascinating report on sonification, Bill. We'll have more on that at the end of tonight's episode. Well, I've got some headlines for us now, so let's turn to those. So right off the bat, first of all, the asteroid Apophis that for a long time, folks have been talking about it might run into Earth. It's been on a dangerous asteroid list, has been determined to be no threat. That's right, they've made some new radar observations that you're seeing here that show it's not going to run into us. Next, the Orion Nebula had a very interesting study done with it. As you can see here, that beautiful star-forming nebula is a gorgeous thing, is actually a small part of the Orion constellation. You can see here are the three stars of the belt going across the middle, the bright star Betelgeuse up in the left, Rigel down in the lower right, this beautiful pink arc that you can't see with your naked eye, but that's called Barnard's Loop. And now the subject of the study I'm going to tell you about are all these little yellow dots, 304 of them. Protostars, very young stars that are just forming, were studied with the Hubble Space Telescope and the Herschel Telescope to find out how the cavities of gas and dust around them evolved as the stars formed. Now, common wisdom would say the baby stars in this picture, do you see them? Well, here they are, the baby stars in this picture. As they evolve, common wisdom said the cavities should get bigger. The areas should be blown out as the star got closer and closer to being a full-blown star. Well, it turns out that the cavity size didn't change. There was no correlation between it. So there's something going on here we don't fully understand. But we will. We'll study it some more, and those cavities aren't being carved out like we thought they would. Very beautiful objects, and good work by Hubble to dispel what we thought was the mechanism of how star birth stopped. We'll have to figure that out. In another study, the Event Horizon Telescope has measured the magnetic fields in a black hole. Now, you might forget what the Event Horizon Telescope is. I'm showing it here. It's actually an array of dishes that were all used together to form a beautiful image of the black hole in this galaxy. This is M87, biggest galaxy in the Virgo cluster. We have it on our very own big picture in the Gunther Depths of Space. And that blue stuff you're seeing is actually a jet of material being ejected from nearby the black hole. The black hole accelerates material and forms this jet. Well, the Event Horizon Telescope was used to take this beautiful picture of the black hole. Well, the material surrounding the black hole. The black hole is the dark shadow in the middle. The material surrounding it, it's brighter on one side because it's moving towards us. This other side where it's a little fainter, it's moving away from us. Now, it's quite a complicated image, but they've gone in and used what's called polarization to measure the magnetic field. So let's take a look at how that works. The polarization, usually of light, is sort of random, comes off in all different directions. But if you have a polarizer filter, sometimes your glasses will have a filter on them. If you have a pair of driving sunglasses, that'll block out some of the polarized rays. Cameras will have those. You can install them to block out rays. Well, they've used that polarization in this Event Horizon Telescope to measure the magnetic field strength in the black hole, as you're seeing here. So let's put that polarizer in front of it. And as we rotate it around, we'll see that the distribution of light changes around that black hole. So it's polarized differently depending on how we choose to view the polarization angle. So the polarization angle is actually the angle of the direction of the magnetic field and electric fields. It defines those. Like I said, it's normally random, but in this case, they were able to use that polarizer to measure what we see right here, those magnetic field lines spiraling around the center of the black hole. But how does it compare to the models? Is it what we expected? It's what an artist might expect, but what did physics expect? We can see there on the right the model, which was higher resolution at first. When they blur it down to the resolution of what we expect, indeed, it matches pretty closely. So our physics, our understanding of what's going on around that black hole is pretty good. Now, I can't wait for better and better resolution to see if our details are correct or whether just the general understanding is correct. That said, great result from the Event Horizon Telescope. Now, a star that's dusty, another star companion around it. This is a really crazy looking image. It's a star called U Monocerotis. I have a terrible time saying this. Anyway, it's a star in the constellation of Monoceros, and it has variability to it. It gets brighter and fainter and brighter and fainter in this sort of weird pattern. You can see up above more than 10,000 days of observations are there, and there's periods where it's very faint for quite a long period of time, and then other times it goes up and down. In the lower panel, you can see a zoom in of the region from 6,000 to 7,400 days, and there's even a smaller period in there up and down. So this star is really complicated, hard to understand. Well, some researchers went in and decided if they use a disk, a debris disk, and put two stars, a blue star and a yellow star that's actually evolved. It's a little bit further along in its evolution. in a close orbit together, orbiting very close together. As you can see, their orbits are much, much closer than even the distance to Voyager 1 is from the Sun, closer than the distance of Neptune. When you put them in there and put them on an orbit, they grab onto some of the gas that's in that disk. They glow, they give off X-rays. It's a very interesting system. Let's take a look at the video here of what we think is happening in this system. First of all, a view from kind of up above to give us a picture. We can see the two stars orbiting, the blue star that hasn't evolved as much. They both grab onto a little material when they get near the edge there. You saw that. So the brightness varies, goes up and down. Now one of them is hidden. The yellow one is hidden behind that dust cloud, so it gets faint for quite a long time. Then you can see both of them again. And the yellow one actually pulsates naturally as another consequence, is what they're showing here. It's a consequence of its age and the star type. So very complicated system, a blue star that hasn't evolved yet, still grabbing onto some material. The yellow pulsing star grabs onto material as well, and they're both enshrouded in a disk of dust. Very complicated system, but the researchers did an amazing job modeling this and figuring out what could possibly explain this crazy light curve. So that's a few of the headlines from around the astronomy research that's been done this month. But Patrick saw something that Juno did while out at Jupiter that was a little unusual. Patrick, what's Juno done now besides beautiful pictures?
Well, Juno may have solved something with this image, which is the zodiacal light. The zodiacal light is seen only long after sunset, and it's a lingering twilight, or what people have called false dawn, or even false dust. It's a cone of light that stretches from the horizon and goes up along the constellations of the zodiac. Astronomers have debated what is the cause of this light that they see in the evening sky, or even in the morning sky. And what they think it is, and it's hotly debated, is perhaps it's dust from asteroids that have collided long ago, or even dust from comets that have been shed in the solar system. But recently, as we mentioned, Juno made an interesting discovery. Juno was launched in 2011, and as it circled away from the Earth, it made a deep space maneuver outside orbit of Mars, and then that deep space maneuver took it back towards the Earth for a flyby and a gravity assist from the Earth, and then along to Jupiter in 2016. Now, this is interesting because during that time, when it was moving in between the orbits of Mars and Earth, the Juno spacecraft solar panels were hit by microscopic dust particles. And these dust particles were hitting the solar panels at roughly about 10,000 miles per hour. They were actually observed by the star tracker instruments. Here we see an image with 3 stars, reference stars, that are used to orientate the Juno spacecraft. But the object in the red circle is actually debris that was dislodged by the impacts of the dust. Now, from the instruments on Juno, investigators were able to make a map of the distribution of the dust that Juno had encountered. And they found something very interesting. They found that the dust is actually centered around the orbit of Mars and is densest closest to the orbit of Mars, suggesting that Mars could be the source of the interplanetary dust that causes the zodiacal light. Now, we know that Mars has dust storms, and when it's calm, you can see most of the surface of Mars, as you can see in this image taken by the Hubble Space Telescope. But at right, when a dust storm rages, it can cover the entire planet with dust, and then markings will be very difficult to see. So in effect, the dust particles that cause the zodiacal light have been traced back to the planet Mars. The question the scientists now have to answer is, how can the dust leave the gravitational field of Mars and go out into space and produce these beautiful zodiacal lights that we can see in the evenings, especially in March here in Northern Hemisphere, and also in the mornings in November in the autumn.
So Patrick, are spacecraft going to have to worry about this zodiacal dust when traveling to Mars and beyond for future missions?
That's an excellent question. In fact, the distribution of dust that's being mapped out by Juno actually provides a way of knowing where the dust is densest. And so for future spacecraft traveling out from the Earth, past Mars and onto Jupiter or even beyond, they will know how to craft an orbit that will avoid the densest distributions of the dust. And mainly it's around the orbit of Mars.
Wow, super, super fascinating. We'll wait to see more about how they use this information. Now, Juno, as we all know, is we're used to seeing beautiful images of Jupiter's atmosphere and clouds, kind of like these ones you see here. But Juno, in this case, showed us the zodiacal light, so something different, and also recently, an observatory on Earth told us something about Jupiter's wind speeds in those clouds we're seeing pictures of. Patrick, what was that all about? And what Earth Observatory is making these observations of Jupiter?
Okay, well, this is a very interesting story involving Jupiter's upper winds. Normally, we can estimate the speed of the winds just by looking at the visible clouds and seeing a movement across Jupiter. How do you estimate the speeds of winds that are not visible, that are above Jupiter's clouds? So that was an interesting project for scientists to figure out. So what they did was they used ALMA, which is the Atacama Large Millimeter Submillimeter Array. This is basically a collection of 66 radio telescopes. They actually used 44 of them, aimed it at the planet Jupiter. And they were looking for a particular molecule in Jupiter's atmosphere that's uncommon to basically Jupiter's atmosphere itself. It's a molecule that was left over from the Shoemaker-Levy 9 impact back in 1994. This was a comet that slammed it into Jupiter and left some markings on Jupiter that were visible even from moderately sized telescopes here on Earth. What they were looking for in Jupiter's atmosphere is a molecule called hydrogen cyanide, which is present in comets. And this was still in the atmosphere of Jupiter. And what they wanted to do was to find how fast these molecules were traveling above the cloud tops of Jupiter. And they got a measurement, and it only took them about 30 minutes of observation. They found that the wind speeds above Jupiter's cloud tops was 900 miles an hour at the polar regions, which was a very surprising finding. The predictions was that the wind speeds decreased in the stratosphere. And what the scientists found out was it was quite the opposite. They swirl around in a vortex, which is roughly about 4 times the Earth's diameter. This is a huge jet stream that's swirling around the north and south pole of Jupiter. And it's a very surprising finding for them.
It's always great to see observatories from different aspects, Juno at Jupiter and ground-based ALMA, used kind of in conjunction to figure out what's going on at Jupiter. This is the modern era of research, using everything we can get our hands on. And speaking of getting his hands on things, Chris Butler is out to launch once again and has his hands on a bunch of interesting footage for us. What do you have for us tonight?
Well, actually, we've got an awful lot. It's exciting stuff, maybe the most exciting kinds of stuff there can be with launches. Now, space probes, satellites, telescopes, all of them are exciting. But there's nothing much more exciting than launches involving human beings, human space flight. And we got a couple of those and stuff leading up to human space flight all going on this month to pay attention to. So let's launch right into it. First things first, we've got the old space launch system. The Space Launch System is the rocket NASA has been building for a very long time. This is a rocket that's intended to take human beings back to the moon and maybe even farther into deep space. It's a big deal. They've been building this rocket for a long time. Now, it's had its critics because it's taken a long time and it's been over budget and so forth, but they had their first really important test of what they call the core stage, the center part of the Space Launch System. They put it up on a test stand on March 18th and tried firing its 4 engines. Now, they'd done that just last month previous to that, and they had to cut off. They didn't get the full length of the test that they wanted. But on March 18th, when they pressed the magic go button, everything indeed worked. The rocket is over in the test stand that you see to the right. You can see the orange top of this core stage. The 4 giant engines at the bottom of it are firing down into a trough of water, which is exploding into steam. That's what you see, that big cloud going off to the side. They fired the engines for 8 minutes, and it worked this time. They're feeling a lot more confident about the Space Launch System. And so this stage, now that it's been verified to work, is going to be sent from Mississippi, where this test was done, to Florida, to the Kennedy Space Center in the Vehicle Assembly Building, where they're going to attach 2 giant solid rocket motors that are waiting for it, boosters like the ones the space shuttle used to have. And then after that, they're going to put on top of it the Orion spacecraft. Now that's meant to carry people. It won't carry people on its first flight, which is aiming at November of 2021, but it will be a flight around the moon, orbiting the moon, a spaceship designed to carry human beings. So if that flight, which is called Artemis 1, is successful, then down the road, maybe another year down the road, we'll see, they're going to try putting people on it, and it'll be the first flight of people back to the moon since I was, I think, 8 years old. So this is pretty exciting stuff.
Quick question for you, though, Chris. Is this
Yeah.
something you think we can be thankful for maybe next Thanksgiving, where we're going to be able to see
Yes.
some footage of an American spacecraft designed to have humans in it on the far
Yep.
side of the moon? Now, that's
Yeah.
great news.
Oh, absolutely. You think about that. One of the pictures we have seen all of our lives is the Earthrise out the window of an Apollo spacecraft. Well, Orion is essentially the Uber Apollo. It's a bigger version of the Apollo, but we're going to see that again on live television. And knowing that people are going after that, it's really exciting stuff. And it's about to happen. So fingers
Fantastic.
crossed.
Now, like you said, there are other big rockets out there.
Well, now, there are competitors, of course, in all of this. Just in recent years, SpaceX has come to the forefront, and they are now building the Starship. Now, the Starship is every bit as big as the Space Launch System. They're both rivals to the old Saturn V that we remember from the Apollo program. SpaceX, however, is building a rocket that's designed not just to be able to go up into space, but also to come back and be reused. The old Space Launch System that they're building is a traditional rocket that's thrown away. Only the Orion spacecraft would come back. So what SpaceX has been doing down in Boca Chica, Texas, in South Texas, is testing something that's even trickier to do. They have their new version, their new test article of the rocket, which is serial number 11. Now, to remind you folks, the first full-up test article was serial number 8. 8 launched, went up, belly flopped as it was supposed to, glided back down, turned around, tried to land, and blew up. Serial number 9 launched, went up, belly flopped, came back down, and smashed into the ground and exploded. Serial number 10 launched, belly flopped, came back down, landed on its tail as it was supposed to, sat there for 8 minutes, and then exploded. All right, so the question is, what about serial number 11?
Ignition of all 3 engines, and let's watch and see what happens with the landing.
Okay.
They're at a kilometer in altitude, so here we go. Engines are getting ready. Here they go.
There was an orange.
Look at that.
Whoa!
Did it?
Our camera.
It hit the ground. Okay.
Our camera. Flying debris and pieces of Starship. There's stuff smoking on the ground in front of the camera. I switched to it here. We didn't get anything from SpaceX.
Ah! All right, that was not ideal. Okay, however, take the long view on this, folks. This is a really tricky thing to do. This isn't simple at all. They're going to have to continue with tests, of course, but they're going to continue with the tests. SpaceX was the first company ever to learn how to land a rocket of any kind coming back from space like that. So remember, they've done this work before, and that's why we test, as they always say. So they'll go right back out and try again with a new rocket, and hopefully this time it'll work.
Yeah, well, and let the folks at Boca Chica, they're getting tired of hearing those explosions. I'm sure they're looking forward to the day it works as much as SpaceX is. But what else has been going on out there? Anything else for us in space news?
Yeah, absolutely. One thing I want to mention with regard to the Starship is that, of course, there might have been a little bit of jealousy between SpaceX and NASA on this. And for the very first time, we have got some of the NASA astronauts coming down to visit the big rocket. And here we have a nice post by NASA astronaut Christina Koch talking about how they're paying attention to what's going on with the Starship. Who knows? In 5 years, maybe one of them's going to be riding on that monster. So with the Space Launch System having had some schedule and cost overruns, there's a possibility that NASA is going to invest more heavily in this rocket as well. So that's an evolving relationship, and a sight of astronauts standing in front of that rocket is kind of a neat thing to see. But now that's not all we have. I should tell you, there's also the question of the big, gigantic booster stage that goes under that. SpaceX is building that too. They're building the first test articles. So in 2021, we're going to see the booster stage that goes underneath a Starship also fly. Again, watch the news. These things are being tested very shortly. I also want to call attention to our Russian friends. The venerable and reliable Soyuz spacecraft will be carrying 2 cosmonauts into space to the International Space Station on April 9th. But there's something even a little bit more special about it for those of us here at Griffith Observatory. A NASA astronaut, Mark Vande Hei, will be on board on his way to the station. And astronaut Vande Hei actually has visited us out at Griffith Observatory. He's come to some of our special events, and we consider him a friend of the institution. So a very special bon voyage and good wishes for astronaut Vande Hei and, of course, his cosmonaut teammates on the Soyuz launching on April 9th. Looking to American shores, we have the Dragon spacecraft, the SpaceX Dragon that carries the astronauts to the space station, and we're going to have a launch too. It'll be no earlier than April 22nd. The exact time of the launch, we don't know yet either. Again, watch the news here, and you can see the crew here of Megan MacArthur, Thomas Pesquet, Akihiko Hoshide, and Shane Kimbrough are going to be flying from the Kennedy Space Center in Florida on their mission. And I should say, this spacecraft has been up there before. This is the first reuse of a Dragon spacecraft and the first reuse of a spacecraft to carry people since the Space Shuttle program. This spacecraft has been named Endeavour by its first crew. Astronauts Hurley and Benken had flown aboard Space Shuttle Endeavour, loved her, and so they named this Endeavour. So it's not just a flight for the Crew 2 mission for SpaceX, but also it's a reflight of Endeavour. Good luck to them. For those of you who want to see a launch yourself, if you're going to be staying in Southern California, I do have one possibility for you, and it's just a possibility. Vandenberg Air Force Base is up the California coast in the center of California. You see it marked there on the map, right in the middle. Down below is the bend of the coast that goes past Malibu and all that. Of course, Los Angeles is just right off to the side. When the Air Force launches from Vandenberg Air Force Base, we can see those launches depending on the time of day, whether it's cloudy and so on. And they do have a launch coming up. Now, being a secret military launch, we don't know the details of the time, but we do know that this is the Delta IV Heavy. We talked about the Starship. We talked about the Space Launch System. Well, right now, this is just about the most powerful rocket on Earth. It's a big deal when it launches. We don't know what it's carrying. It's for the National Reconnaissance Office. It's a secret military payload, but it is scheduled to go in April. So if you Google in launches, launch schedule, launches near me, or go to spaceflightnow.com or spaceflightinsider.com, they have a list of schedules. And as soon as the Air Force is willing to announce when this launch happens, we'll have a heads up for it. But just be watchful of that. Keep your eyes to the skies. And in the meantime, I'm out to launch. Thank you.
Well, just a fantastic rocket report. Thank you again, Chris. The Delta IV, I've always wanted to see one of those in-person launch, which maybe I'll try and get up there and see it. Unfortunately, at Vandenberg, there's not a vantage point for the public that you can see the engines ignite. The Delta IV does something super interesting. A bunch of the fuel is sort of surrounding the rocket as it launches, and it looks like it lights itself on fire. It
looks really bad for a moment, doesn't it?
It sure does, but there's nothing wrong with it. That it's doing what it does.
True.
But take a look for this launch if you're in the area. There are places you can get to, but don't expect to be able to drive onto the base. Don't expect to get too close. But if you do a little Googling, you can find a place where you have a clear view once it clears the hills and you get to experience the rumble. It's great fun. We've got some exciting news from Mars with our Perseverance rover, of course, and the Ingenuity helicopter that hitched a ride along with the rover to Mars. Now, just in case you haven't been paying attention, Perseverance is a rover. Much like Curiosity, it's been delivered to the surface of Mars right here. And you can see, let me mark the position where the rover landed right here. Now, why are we so interested? Well, you can see this delta deposit from where this river flowed in to a lake. This lake was about the size of Lake Tahoe, give or take. And it's dry now, obviously, but deposits were left behind that even perhaps could have signs of life left over inside them, chemical signatures that life would leave there. Well, they've chosen a couple possible paths for Perseverance to take, maybe the blue path to get to that delta deposit, or perhaps the purple path. I'm not exactly sure how they're going to decide. It'll have to do with science. Which direction has the most interesting science targets to take, and also safety. Which direction has the safest path to get to our main science? Meanwhile, of course, the rover itself has indeed been taking some spectacular photographs. That is the delta deposit off in the distance that you can see there. This big rock in the foreground that I'm circling with the laser pointer right now, that is a foreground rock. It's only about 6 feet long. That delta deposit is much, much larger. Something about 6 feet long would only be maybe from there to there. So in addition to taking beautiful images with the cameras, scientists have been testing out the rover itself as well. Here's Perseverance's wheel, sort of twisting back and forth in the Martian dirt. Here, leaving some tracks behind, like our special guest, Nagee Cox, last month, told us that she was rolling. And indeed, Percy's been leaving tracks in the dirt. Not only that, scientists have been putting together the hazard camera frames and giving us little movies to take a look at. So here she is driving around, backing up. You can see the track tires that were there. Pretty fun stuff. Driving around little U-turns. You can see the actual color of the dirt there. And in the upper right, that indeed is where the surface of Mars was blown clean by the rockets. And on the left-hand side, right above the rover, you can see where the rockets on the left-hand side of where she landed blew the surface clear. Other instruments have been tested. Here, the robot arm is being worked out a little bit, spinning it and showing that the joints can flex. In this image, boing, a little canister has been opened up there so we can protect, I think it's a sample container. In addition, Perseverance has been leaving stuff behind on the surface of Mars. I know everywhere we go, we litter. Our robots are littering. What have we come to? Well, we need to do this. This protected the belly of actually the sample gathering unit of Perseverance is on the belly side. So this protected it during landing. They popped that off, and then they actually also popped off the section covering the helicopter, like you can see here, the dust cover of the helicopter. So the sample protector, the belly protector went there, and that whole region, now they're able to access, they're able to put in the samples, they're able to interact with, and right here is Ingenuity on the belly of Perseverance still. And here you can see they've even chosen the airfield and the flight zone for Ingenuity, which was shockingly close to the rover landing location. Well, not that surprising. A nice big flat area is a good place to land. Big flat area is also a good place to fly. And as you can see in this shot, sort of a three-quarter view, the Van Zyl outlook is the location where the rover is going to drive and watch the flight operations of the helicopter Ingenuity down below. So Perseverance will record those flights as they happen, and we'll get to see some views. Right now, this is the view of that area. You can see the main takeoff zone of the helicopter. So Perseverance needs to drive there, drop off the helicopter. It'll take several days to unfold and have everything placed. But once Ingenuity's on the ground, they only have about a day to drive off, or the solar panels and the batteries on Ingenuity won't do what they need to do and keep it charged. It'll die in the cold. So they need to have Perseverance roll off the top of Ingenuity to make sure those solar panels get sunlight on them before the batteries die on the helicopter. So that'll be what they do right away once the helicopter's dropped off. And here's that same view of the flight zone without the annotations. Now the helicopter itself, when it's used, it'll take off, do a little loop, come back down and land, but it'll investigate some new areas. Now it might be able to take off and go to a potential new landing site if everything looks good enough. But I believe the first plan is to do a safe flight up and then come back down and land in a safe location. It's not going to go very high up, only handfuls of meters to start. And then later, once they get the handling of the helicopter and everything worked out, maybe they'll take some more risks. Perseverance herself has found the first science target. It was named after the Navajo word for Mars. Ma'az, I believe, is how you say that, although apologies. My Navajo is not so good, but I find it wonderful that we're honoring other heritages, other cultures that have celebrated astronomy and the planet Mars in our skies. So we have gotten our first close-up view of that target, and it looks like, I don't know, water maybe worked on this, or I don't know. I have no idea how to interpret these images yet. And that's what's exciting, is these things haven't been very well interpreted by our scientists yet. The papers haven't come out. Well, here is a multiple view. We have our NavCam context view, our SuperCam mosaic of another target, Yigo. And you can see here another small area, and our Mastcam Z zoomed in and was able to see that up close. So take a look here. Here's this tiny rock in our navigation camera. Here it is, and you think, well, that's pretty good. That's a good zoom. Well, no, they're able to take this much smaller region and see very fine details, and even differences at what looks like in the minerals in that rock. So these are the capabilities these new cameras are bringing to our research on Mars. Now, interestingly enough, Curiosity has been doing some work herself over in Gale Crater and on climbing up Mount Sharp. You can see this layered structure here. This rock was laid down over a very long time as Mount Sharp was built up in this crater. Well, those layers are what tell the story of the changing climate on Mars, and Curiosity is making those measurements now. Well, the climate on Mars, we might think, well, it's got to be cold. It is 1% the Earth's atmosphere, very, very thin, although there are clouds. And as you can see here in this next shot, Professor Paul Byrne made this post and stunningly put together a bunch of raw images, and you see clouds floating in front of that rock, in front of that layered rock I was just showing you. And in fact, they were caught in action, as you can see here. The interesting things you can see on Twitter exploded, actually, and here's a color picture of those same clouds behind that rock. Now, clouds are seen from the sky on Mars, and as you can see here from the Trace Gas Orbiter that was sent to Mars, you see some clouds over on the right-hand side, but you're also seeing frost-covered sand dunes. So super, super interesting structures. The dark colors in this image are actually where the frost has sublimated away into the atmosphere and shown the dark basalt underneath. So as the frost sublimates away, more and more dark lines will appear in this image, and those dark lines generally show you the direction of the wind. They run perpendicular to the wind flow. So very interesting patterns in these dunes. They tell us about the Martian climate, but we have seen also other interesting clouds from space, and Patrick So is going to tell you all about one that recently they did a little bit of work on and kind of learned a lot about it. Patrick, what's this other strange cloud in Mars's atmosphere?
All right, well, let's get to the picture of this strange cloud. It appears on Mars as a streak and has been seen by various orbiter missions to the planet Mars. In fact, since Viking 1 back in 1976, produced images of this kind of cloud that is very long and very unusual for Mars. We've seen earlier that when David was showing those other clouds, usually our normal clouds are very thin and cirrus-like. But what is this? And it has baffled scientists for many decades. Okay, so as you can see in this view, we've named the features on Mars, and in particular, this cloud is close to a volcano, an ancient volcano called Arsia Mons.
So this is a sign that that volcano is erupting. Tell us all now, Patrick, right?
Yes, this has been so this is why scientists are baffled, because they think, well, is this an active volcano that's actually ejecting a vapor, smoke, or some material into the atmosphere, and we're sealing the trailing edge. But actually, just a recent paper has kind of demystified what this feature actually is. And we're going to go to the next slide where we're going to show you a whole bunch of information. And so we're going to break this down for you because it looks complicated. But the paper kind of explained what the origin of this long trail plume cloud is on Mars. So let's go ahead and break these sections down here in this image. First of all, what's happening is that the wind of Mars is actually blowing against this volcano, and the air is on Mars, even though it's 1%, is forced up rapidly to a height of roughly about 28 miles, which is about 4 times higher than a jet airliner at altitude here on Earth. And that air actually contains moisture. It contains water vapor. And that water vapor being forced up to the colder regions of Mars's atmosphere freezes out and condenses, and you get that cloud that you see. And what we see here in the next image is kind of the structure of the cloud. It forms a head, and then there's this long trail that's roughly about 1,000 miles in length. The width of the cloud itself is roughly about 75 miles across. How it forms is very interesting. Below here, we see a timeline, and we're going to start with the first rectangle there. The cloud actually starts as a kind of like a circular feature just before sunrise, and these times here are Martian times, so just before sunrise, roughly about 5 a.m. And then 2 hours later, it grows it grows the tail. And this tail actually grows very quickly. It speeds up from the origin where the head is at roughly a speed of about 300 miles an hour. So that's how quickly it grows. And then later in the day, the cloud has become its full length. But by the afternoon time, as the sun warms up the surface of Mars and warms up the atmosphere, those ice crystals, which is what this cloud is made of, begins to dissipate and become water vapor again, and becomes invisible. Now, the cloud itself was observed recently by Mars Express. And in this next image, we're going to look at observations made by Mars Express back in 2018. And you can see how this cloud evolves. Here we're seeing the blue line, which represents the terminator of Mars, which divides the night and day of Mars. And there's early morning, and you can see how it grows during the day, and the cloud kind of wavers off to the west of Arsia Mons, and then eventually dissipates. So in this image, we can see the full extent of the strange-looking cloud. Is not from a volcanic eruption. These volcanoes have been extinct for billions of years. But what we're seeing is basically an orographic cloud where air is forced up in the air and kind of freezes and then trails away from the westward side of the volcano. One of the interesting things is that understanding how this cloud forms gives us a model of of Mars's atmosphere and its dynamics. And also we can compare that to the Earth's atmosphere as well. And it proves our models of climatic conditions on both Mars and the Earth. So this is very great research and solves the mystery of this cloud that's formed on Mars.
Yeah, well, thank you so much for that, Patrick. Again, a wonderful feature on a interesting cloud, but this one in Mars's sky. So now, if folks want to see Mars, Patrick will tell you just how to do that as part of tonight's Sky Report. Patrick, take it from here.
Oh, that's right. So we're going to take a look at some of the things you can see in the sky. In particular, we're going to start with April 6th. And if you are up early in the morning, you're going to see Saturn and Jupiter. But in particular, the 24-day-old waning crescent moon will be roughly about 5 degrees below Saturn. So that's how you're going to identify Saturn if you've never seen it in the morning sky before. Now, if you miss that, you can go out the next morning and see that the moon has moved below planet Jupiter. And again, it's roughly about 5 degrees from Jupiter. Now, just turning to the morning sky in general, in the middle of the month, if you look around, you will see, particularly to the south, you're going to see many of the constellations that normally are visible during summer evenings. The morning sky is really a season ahead of what you would see in the evening sky. So, for example, looking south, you'll see the bright star Antares, which marks the heart of Scorpius the Scorpion. And there are a number of other bright stars to the southwest. There's Spica, and there's also Arcturus. And there's also this faint band of light that runs across the sky, which unfortunately is not visible from Los Angeles because of all the bright city lights. That band of light that runs from Antares down to Sagittarius is called the Milky Way. And here I've indicated it with, there's a line that you see that runs right across the Milky Way. That line is the equator, or the galactic equator, of our own Milky Way galaxy. The center of the galaxy is marked by that blue star, and it's just above the constellation of Sagittarius. So if you could see that portion of the Milky Way, that is the brightest portion of the Milky Way that you would see in the entire night sky. As I've said, you can't really see the Milky Way from Los Angeles because of the bright city lights. You really have to go far away from the lights where you can get clear, dark skies. Here's an image taken by Anthony Perkett, one of our telescope demonstrators, from Joshua Tree Monument, showing the Milky Way rising there. So that's where you see it if you go out camping or planning to, and you're in a dark sky area, a national park. Take in the beauty of the Milky Way. Now, turning to the evening sky, we see many of the constellations and stars of the spring. We'll highlight a few of them. One is the bright star Regulus in the constellation of Leo the Lion. And Leo, actually, the head and the mane, is made up of a bunch of stars which form a backwards question mark ending in the bright star Regulus. Another star that you can see is in the next constellation over in the zodiac, which is Spica in the constellation of Virgo the Maiden. And that's kind of low in the southeast. And then turning a little bit higher in the sky, once again, the orange star Arcturus in the constellation of Boötes the Herdsman. So these are just a few of the stars and constellations you can see in the evening sky. And then turning to Mars, where can we see Mars? Well, currently Mars is in the constellation of Taurus the Bull. And on the 16th, just around about 9 p.m., Mars is just above the waxing crescent moon. So if you have a chance to go out and take a look that evening, you can see Mars and the moon together in the evening sky. And just to give you an idea of how close it is, Mars and the moon will be separated by 4.5 degrees. The constellation of Orion is now sinking slowly to the west and will slowly disappear in the light of the sun by the end of the month. The Lyrid meteor shower peaks on the night of the 21st to the morning of the 22nd, and the peak hour is roughly just around about 3 to about 4 in the morning. You can see in a clear dark sky roughly about 18 meteors per hour. The meteors radiate from a point just above the constellation of Lyra the Harp, and in Lyra the Harp, the brightest star is Vega. Now, at the end of the month, we're going to get a chance to see the brightest planet in the night sky, which is the planet Venus, low in the west there, and with the planet Mercury just above it. This is a view that you would see just about half an hour after sunset. So both planets are very low in that area of the sky, but if you have a chance to see it, take a look for Mercury and Venus at the end of the month. And now to our moon phases. So we have a last quarter on the 4th, new is on the 11th. First quarter is the 19th, and full moon is the 26th. So that's your sky report. Enjoy and go out, and wish you clear skies.
We should be having folks out there taking a look at the sky. I encourage everyone to get out there. The weather's getting nicer. The evenings are still dark fairly early on, unlike our summer months. So it's a great time to go out and take a look at what's up in the skies. And not only that, people can also take pictures of what's in the night sky. And if you like to do that, tweet at us, send them to us. We've given you our social media, and maybe you can make the pretty pictures with Katie section of our show. Katie, take it away.
Our first pretty picture here is called Hubble Captures Re-Energized Planetary Nebula. This is located around 5,000 light years away in the constellation Cygnus the Swan. Here we have some vultures captured in Joshua Tree National Park from telescope demonstrator Anthony Perkic, right before he was imaging the night sky in mid-March. Here we have the Summer Triangle Rising by Anthony Perkic, and the Milky Way Rising. This is Galaxy M105 in constellation Leo, gorgeous picture. And Galaxy 104, M104, the Sombrero Galaxy, which is in constellation Virgo. And Galaxy M83, the Southern Pinwheel Galaxy. This is in constellation Hydra or Centaurus. And on the left, we have Galaxy M53. On the right, you'll see NGC 5053, and these are in constellation Virgo. Now, these beautiful images coming up are from David Pinsky. These are taken on March 11th on the trail to Mount Hollywood. Another lovely image from David Pinsky of the ISS Pass. And here we have the first quarter moon taken on March 21st by David Pinsky. Here is a gorgeous image of the full moon in March that happened just last weekend. This is also known as the worm moon. Now this is an image of an algae bloom in Lake Utah. And about every week, sometimes more, scientists from Utah State University check for these fast-growing algae blooms. And these are made up of naturally occurring algae, phytoplankton, cyanobacteria, and these may be harmful to people and pets, which is why scientists are measuring them. And the problem is that many cyanobacteria produce toxins, and that's from Kate Vikas of Utah State University. Now this is Landsat 8. The satellite is the satellite that they use to help detect when a lake changes color. And because it can detect color, it detects the greenish color produced by these algae blooms. So the conditions needed to create something like this are warm temperatures, a lot of nutrients, and calm waters. And many of the bodies of water in Utah meet these conditions, especially with warming temperatures, which are due to climate change. And another satellite that helps scientists measure and understand water on Earth, specifically the water cycle, is ESA's SMOS satellite, which measures moisture in soil and salt in surface waters of the ocean. Due to SMOS's wide field of view, it is also able to detect radio bursts that are associated with coronal mass ejections from the sun. And these appear as noise to Earth scientists when they're measuring these water components on Earth, but they are extremely important for space weather measurements. So space weather is variations in the environment between the Earth and the sun, and these are caused by solar flares or coronal mass ejections in solar wind. And scientists found that the sun signals that appear as noise actually help monitor solar activity. So this is extremely important data to have because space weather can damage communication and navigation systems such as GPS, as well as other satellites. So our last pretty picture, I found it appropriate to be of the sun, and this was taken by Anthony Cook over Pasadena around 2:30 p.m. PDT, and this was taken on March 29th.
Thank you, Katie. Always a pleasure to see the pretty pictures with Katie. And if you out there in our audience have a pretty picture you'd like us to show or you'd be willing to share with our audience, tweet at us, send it to us. If you're an astrophotographer or just capture a beautiful sunset, let us know and we'll maybe include your work. And now, speaking of work, we're happy to turn to our guest segment, and to introduce that, we're going to take a look at a trailer for her latest work that was all over the internet. Take a look here. Ladies and gentlemen, we're super pleased tonight to have with us Dr. Michelle Collins from Surrey. Now, is that Surrey University in the UK? What?
It's the University of Surrey.
University of Surrey. Well, how exciting is this? Now, you're currently there you're in Surrey right at the moment. You didn't fly to LA during all this COVID, did you?
I did not know. That's expressly forbidden at the moment. We're not allowed to travel outside, really, our own towns at the moment.
Most places, Americans can't go anywhere either in general. So,
yeah, good. Well, then we're breaking no rules.
Breaking no rules. Well, thank you so much for joining us virtually, shall we say, over the internet. Now, we played the promo video that you made about your new paper. So, yes. What is a little bit of the story behind that, if you can? And also, what do you do at university there? You're an astronomer, I know, and you've been doing research, but you also teach. Tell us a bit about yourself.
Yeah, so I've been at the University of Surrey now for almost 6 years, and I started. It's my first permanent academic job. Hopefully, my last as well, if everything goes well. So I started as a lecturer back in 2015. I was recently promoted to senior lecturer, which is so we have a very different scale here. Where I think in the US I would be considered a professor by now, but for us you have to really age to about 70 to be a professor or something, it seems like. So but I'm at sort of an equivalent level here in Surrey, and so I'm an astronomer there. So I work in a physics department, and my job is part teaching for the undergraduates, and then also research, both through my own research and also with PhD students and postdocs as well.
Well, awesome. Fantastic. So now, what is the story behind the promo we saw in the video? It's quite fantastic. It made a lot of folks on Twitter excited, I know, and I thought that night we need to have Dr. come on as a guest. So, and by the way, I like to, here at Griffith University, here at Griffith Observatory, we do actually like to use our honorifics like doctor to show off the hard work you did to get in this position. I know our own director, Dr. Kropp, likes to do that, so I'm going to honor it that way. But of course, I've known you for a little while, but I didn't know you were so talented at making these promo videos. So what happened with this one?
Yeah, so it was actually just a bit of a throwaway kind of fun thing I did. I've been working on this particular paper was something I started back when I was working in Heidelberg in Germany in 2013, 2014. I got some really exciting data in, and I started writing a paper back then. And it was kind of almost in a stage where we could think about publishing it. But then I moved to the US for a new job. And I was just there for 1 year before I moved again to the University of Surrey. And so it was just a very kind of turbulent time where I was getting used to new places, starting new projects and new collaborations. And this paper was just kind of always simmering along, like in the background, like something I would keep going back to and not quite getting done. And then, of course, the longer these things drag on for, the guiltier you feel about it. So, the less likely you are to want to open it up and see what you last wrote like 3 months ago when you thought about doing anything with it.
So did any of your colleagues, any of your co-authors on the paper, were they pressuring you to get this done? And did you keep any emails from them unopened for months at a time?
It was sort of the other way around. I think the last stage I had, I'd sort of like pushed the ball back into a couple of people's court to do some modeling. So I'd got the observations, I'd done the analysis, and we'd done some like preliminary models of the data. But we were thinking about what the next step was, and that was not really my territory. So that was where we left it. And so luckily, I was not the last person left with an action item. And actually coming to the University of Surrey was great because my colleague Justin Reed is actually super good at this modeling stuff. So we started talking about it, and he was like, oh, my tool will work great for doing the model of this galaxy, this little galaxy. And we can learn about if its dark matter is really lower density than we expect, which was the exciting thing about the object in the first place, is that it seemed to be lower mass than we thought it should be. So then he was able to help me do the modeling. Well, he did the modeling, and like he joined the paper, joined the team. And in the end, like that 7-year delay, I think totally made it a much better paper than it would have been had I published it in 2014. But, it felt like this massive journey and a thing that I'd been just like in the back of my mind for so long. So when I submitted it, I was like, well, great, now it's submitted. I want to do like a little celebration. And I'd seen that iMovie has these little movie trailers you can make. And I was like, I wonder if I can make a movie trailer for my paper. And it turns out it's super easy to do. Like you just give it a bunch of images and like write a couple of captions, and it does everything else for you. So I just took a bunch of screenshots, some of them serious, some of them less serious. Like my favorite one is where the appendix scrolls across. It's like one of the least interesting parts of the paper, but it has its own special like swipe. And so I made it, and I was just, I thought it was hilarious, but I often think things I do in lockdown are really funny, and not everyone else gets it. So when I was done, I just put it on Twitter, and I expected to get like a handful of, of likes. And it just kind of blew up. So my Twitter was like just endless notifications of people really enjoying it and really appreciating it. So it ended up being far bigger than I had envisioned. And a few other people have started making trailers since. So I worry that I've created a thing that we'll all have to do every time we publish a paper now.
I fear you have done that. And I also fear that now, before every talk and colloquium, we'll have to watch, 10, 15 minutes of trailers of future papers.
Yep. Yeah. It's going to be just like a trip to the cinema. Yeah. We'll also start selling really expensive, like snacks. To bring in a bit of extra travel money.
If you want that Mars bar, then you're going to have to pony up the cash. And that joke works both across there and here, by the way, but don't expect to be the same candy bar if you ever travel here.
Yes. No, I've experienced that. It's very different.
Yeah. Anyway, back to the paper. You study I did. I still do a little bit here and there. I dabble, but you're still deeply involved in research in the local group, and both of us love the Andromeda system of galaxies and Andromeda itself. I know it's dear to my heart as well. It's my thesis galaxy, as you know.
Yes.
But you have studied a whole bunch of the dwarf galaxies around Andromeda. And how many of them are there now? And which was the target of your most recent paper?
Yeah, so I think in total, there are 35 dwarf galaxies, of which I think 31 are dwarf spheroidal galaxies, which is the type I study. And those are the smallest galaxies we're able to find in the universe. So the faintest, the lowest mass. And they're also super interesting because they seem to have really high dark matter ratios. So compared to like a Milky Way or an Andromeda galaxy, which has, some fraction of dark matter, they seem to be much more rich in dark matter with many fewer stars. So that's why we're really interested in studying them, because they can maybe tell us more about what dark matter is and how it behaves. And the dwarf galaxy I was studying in this case is known as a very catchy name, as most of them are. And this one is Andromeda 21. So I think I'm one of the few people, maybe of only like 2 or 3 people in the world that is intimately like acquainted with every single dwarf galaxy in Andromeda. So if someone says Andromeda 23, I'm like, oh yeah, I know that guy. But no one else does. But Andromeda 21 is one of my favorites. I have about 3 favorites. And it was super interesting, like I say, because while these systems are supposed to have a lot of dark matter, this one was coming up from our initial studies back in 2011 and 12. A seemingly lower mass than we would expect, but we only had a handful of stars to study it with, to get a mass measurement from, and that wasn't really enough. So we went back and re-observed it to get more stars with more velocity measurements, and then you can use those velocities to kind of figure out how much stuff there is in the galaxy. And it still comes up as surprisingly low mass, which is a really interesting finding. And then we have to try and understand what that means.
Now, what is low mass for a galaxy? One of these dwarf spheroidals.
Yeah, so a galaxy like the Milky Way has something like a total mass of around 10 to the 12 solar masses when you combine its stars and its dark matter. So that's like, a 1 with 12 zeros afterwards. The types of dwarf galaxies that I study are far lower in mass. So their total masses are probably more like 1 times 10 to the 9. So like a factor of 1,000, like lower mass in total. But then if you compare the number of stars, it's more like they have, I guess, 7 orders of magnitude fewer, the ones I'm studying, than the Milky Way. So much less bright. And some of the galaxies we find that are dwarf spheroidals are, fainter than a single giant star. They have so few stars that if you look at an image of them, you'd think you were just looking at an image of empty sky. But, to the keen-eyed astronomer, you can see a couple of little dots of light that make up the dwarf galaxy. So they're really, really faint compared to the normal images of galaxies that we tend to see.
Interesting. Now, what goes into getting a mass? You were saying getting velocities for the stars. So what instruments do you use regularly to, first of all, to see the stars, to know where to point telescopes, and then how do you get their velocities?
Yeah, so I'm working or have worked extensively as part of a team called the PANDAS team, which is the Pan Andromeda Archaeological Survey team. And we used mainly 2 telescopes to study Andromeda. So the first one is to take images of Andromeda and its outskirts, so very far away from the disk of the galaxy and out into its outer stellar halo, as we call it. And the telescope we used to do that imaging survey is the Canada, France, Hawaii telescope, which is a 4-meter telescope on the summit of Mauna Kea in Hawaii. And so from that survey data, from that imaging, we can go and look for these little dwarf galaxies that orbit around Andromeda. And once we found them, we then moved to a larger telescope. So we use the Keck telescopes on top of Mauna Kea, which are 10-meter telescopes. And we use typically the DEIMOS spectrograph, which is the Deep Extragalactic Imaging Multi-Object Spectrograph, I think. It's been so long since I've had to say the acronym.
Yeah, not bad.
And that allows us to take, with a single pointing, you can get, you basically take a lot of slits that you put into a big aluminium mask, and each of those slits will cover the position of a star. The light comes through to a spectrograph, gets kind of spread out, so you can then measure wavelengths of individual absorption features. And we know where they should be if those stars were at rest, but they're all shifted. So we can then figure out how fast the star is moving from how much those lines have shifted away from what they would be if the stars were completely still. And then we can use those velocities and the positions of the stars, and then, just simple gravitational laws to understand, how much mass there must be contained within a system based purely on how fast the stars are moving. So if there's not a lot of mass, the stars won't move very fast. And if there's a lot of mass, they'll move a little bit faster. So we just tend to we look at what the random motions of the stars in the galaxy are, and use that to work out what the enclosed mass must be of a system. And then we compare that to what we expect the masses of these systems to be when we consider just, normal, the lambda cold dark matter cosmology that we use in astronomy.
How is it that you can use velocity to tell the Andromeda stars in these dwarfs from the Milky Way ones? What's the giveaway?
So we basically know what the stars. So M31 is currently moving towards us at a relatively fast speed, and so it's quite removed. If you look at how the M31 galaxy is traveling towards us, and then how stars in our own galaxy are moving, they have very different velocities. So you can then assume that M31-like stars will typically be closer in velocity to M31 than they will be the Milky Way. So then you can very easily often see that you'll have, Milky Way-like stars on one side of your graph, and then like a big booming peak of stars with a very narrow width in velocity that is your M31 dwarf galaxy. Now, that's not always the case, but it was the case for Andromeda 21. We have some dwarf galaxies that are very inconvenient, where they have a velocity that is offset from M31 and much more similar to the Milky Way. And this causes us many headaches. But we then have to just be a bit cleverer about how we assign probability to a star being part of the dwarf galaxy versus the Milky Way.
Interesting. So now this Andromeda 2023, you said?
21.
Yeah, not 23.
No, 23. No, forget 23.
Yeah.
That's not interesting.
They get each other's mail all the time.
Yeah. Exactly. Same side of the street. Now, Andromeda 21, is it the least massive Andromeda dwarf you've come across?
So it's not the least massive. It's just seemingly lower density than you would expect or lower mass than you would expect for the number of stars it has. So it's a reasonably bright, for a dwarf spheroidal galaxy, member of the Andromeda 21, the Andromeda system. So it has, quite a few stars. And in general, as a rule of thumb, you expect that the more stars a galaxy has, the heavier its total mass is, because the more mass you have in a galaxy, the more gas you can hold on to, the more stars you can form, the brighter your galaxy becomes. So, more mass means more stars. And you can actually make quite a good relationship between the total mass of a galaxy and the amount of light it has. So then we can kind of say, this galaxy looks as we would expect. This galaxy looks maybe slightly more massive, slightly less massive. But Andromeda 21 is sort of significantly less massive than we would expect based on the number of stars it has. And so that's why we were quite interested in it, because it's hard to explain without invoking additional physics beyond maybe what the standard expectations are for the galaxy.
Do we have an idea of the age and metallicity, the chemical content for our audience out there? How do they compare to the other ones? Is it unusual in any other way?
No, as far as we can tell, not. So in terms of the metallicity and the ages of the stars, they all look very old and reasonably metal poor. And in fact, in that case, it looks very consistent with what we'd expect for a system with that many stars. So the metallicity looks right on where it should be. So the chemical composition is right. The ages look right. One area that it does differ a little bit is it's also slightly more diffuse than we would expect. So a little bit more, its stars are a bit more spread out than a galaxy of a similar luminosity in the Milky Way would be. So almost as if it's kind of expanded away from the norm. So that's maybe a hint into what's happening there, that it has this more diffuse population of stars.
Is there anything in its neighborhood at all? Anything it could have interacted with that could explain this? I mean, obviously, I know there's a big nasty spiral next door. I get that. But how close is 21 to 23 and other things it might have interfered with?
Yeah, so it's pretty isolated, actually. Well, it's still around Andromeda, as you mentioned. So, but otherwise, there's nothing else really in its immediate vicinity that it's likely to have interacted with. Now, we don't know exactly where it's been in the past. And that's quite interesting, because you have this is we think a good explanation for what we're seeing here is, though the galaxy is currently pretty far from Andromeda, it's very possible that if it has quite an extreme orbit that brings it close, then over time, as it comes past Andromeda, it can get tidally shocked, which means the stars kind of can be like compressed and then expand. The dark matter content will do the same. You might strip some of the dark matter off as well in these interactions.
Yes.
And then by the time it moves back out to the outskirts of the halo where it is now, it kind of will expand and just appear like lower density in terms of its stellar component, but also in terms of its dark matter component. And that could be why we measure a lower mass than we expect now. And so that is a good possibility for what could happen there. But it does mean it would probably have to be on quite an extreme orbit.
Yeah.
And unfortunately, because we can only measure how the object is moving with respect sort of along the line of sight. So we only have one component of the motion. We don't know where it's been moving in the past. So if you have 3 dimensions of velocity, like you can measure for some of the Milky Way dwarf galaxies, you can work out what orbit something's on. And then you know if it's interacted with something massive in the past, or one of the smaller galaxies had a flyby with it in the past. You could try and map that out. But for Andromeda at the moment, we can't really test that. But it is a good method. Like it is what you would expect to see if it had had an interaction in the past.
Right.
In rare cases, they'll leave streams behind, and you could just trace out where the orbit is. It's a visual indicator.
Well, yeah, like the LMC and the SMC.
Yeah.
We're not so
That means
lucky.
it has to be right at the end of its lifetime. So by that point, almost all the dark matter's gone. You've stripped the majority of material, and then finally the stars get peeled off into these impressive streams. So if Andromeda 21, though, is in an earlier part of its destruction, then you might not see any of the stars leaving yet, but a lot of its dark matter could already be gone. And that makes it really hard to tell whether or not a dwarf galaxy has been tidally affected. So they may look completely normal, but actually much of their dark matter halo has been gone, just because that's often what goes first.
Mm-hmm.
And it makes it very difficult for us.
So, now, is there an Andromeda dwarf that happens to have a lot of dark matter that's on the other end of the spectrum that's dark matter rich? So the stars are flying around faster than you'd expect them to be.
No, we do have some interesting dwarf galaxies. So there's like the compact elliptical galaxy M32,
Right.
which is very dense in terms of its stellar component. And I think there it's hard to tell what's going on with the dark matter. But that's a super interesting system where the stars are so tightly packed and it's so massive that it's kind of hard to understand how that galaxy has evolved. And some people have recently written a paper that suggests that it's actually sort of the nucleus of a much more massive galaxy that kind of came into Andromeda in the past and has been like all the outskirts are gone and now in a beautiful stream that kind of arcs around the whole of M31. And that's just kind of what's left over. We don't know if that's the case, but that galaxy is super interesting because it does appear really dense, but it's really hard to disentangle because the stars are so dense. We don't know if it's just dense in stellar like component or if it's really an outlier in dark matter too. I think that's the case. I know a little bit less about that galaxy, but it's certainly very interesting and very much the opposite of what we see for Andromeda 21.
32 is pretty close to the disk, is it not? It seems visually to be, but I believe it actually is. I mean, they've got a Tesco and everything. They're right downtown. So, sorry, Breton joke there. Does it seem to have been highly modified, or it's just so strange we really don't know what its story is?
Yeah, it's because what we see now is just sort of almost a perfect sphere, I think, for M32. So it's a really compact ball of stars. So it could be that it had this outer component that's now been completely removed, and that maybe is what makes up what we call the giant stream. But in terms of what we see now, it's just very hard to say. And again, as it's so close to M31 as well, I think it'd be hard to see if there was any kind of remnant sort of stripped population still hanging around the outskirts. So really what you can just see is that very dense central part, I think, is what's happening there.
Do you agree that globulars seem to be thoroughly stripped down former galaxies, or they're their own beast?
Some of them probably are. So some of them will be little nuclear clusters that are left over. But I think many of them are star clusters in their own right. So probably not stripped galaxies for the vast majority of them, I think. I think that's the generally accepted view at the moment. But some of them certainly, like these unusual things like Omega Cen in the Milky Way, is I think the poster child for this kind of weird behavior. And seemingly that was maybe brought in originally as part of a massive galaxy that's now been stripped down.
Yeah, that's where my question of multiple stellar populations goes. In Omega Cen, there's clear evidence of different colored red giant branches, and they would span sort of a range of colors. Changing the subject ever so slightly on this, what do you think is our best chance of learning what dark matter may be comprised of? Do you have a favorite program that's investigating that? Do you have a, what would your money be on if you were in Vegas?
I think some of the interesting stuff that's going on right now, there's sort of two avenues that I think are quite promising. In addition to obviously studying dwarf galaxies, which are super interesting and have been providing some constraints, but we do now know that the stars mess up a lot of our, what we thought would be the easy ways of getting at the issue of dark matter. But for example, one of my colleagues at the University of Surrey, Dennis Erkel, he works on stream structures. So when either globular clusters or dwarf galaxies are interacting with a massive galaxy like the Milky Way, some of them will get destroyed and they get their stars pulled into these beautiful streams that can loop all around the sky. And those that are made from things like globular clusters are really interesting because they tend to form these really thin, kind of pristine looking streams. And what we expect from dark matter is that the Milky Way halo is full, if it's cold dark matter that we have, which is the current paradigm. There's all of these empty dark matter halos that just have dark matter, no stars, no gas, and they're quite low mass, just floating around all through the halo. Now, if one of those punches through, comes into contact with a globular cluster stream, it'll punch through and it'll make a little gap that forms in the stream. And these gaps then, if you find them, can show you that something must have passed through the stream. And if you can show that was a dark matter subhalo, you can start to say, okay, well, we know that dark matter substructure exists in the Milky Way because of these gaps in these streams. And you can begin to constrain then what the mass of these invisible dark matter structures are. And that just really is something that then you can't explain using other physics like modified gravity or something like that, if you can show that they are formed by subhalos. Now, this is quite hard to do, but there are a lot of very smart people working on it. So I think that they can begin to, start to either confirm that something has to exist or rule out certain masses of subhalos using these beautiful streams with these gaps in. But it is very difficult to do. But that's really exciting, I think. I think it can make really competitive constraints and a really great argument for the case of dark matter.
Fantastic. That's very interesting. Now, let's see here. What else? Patrick, do you have any questions you've been wanting to ask?
I was wondering if you've studied dwarf galaxies of our own Milky Way, and and maybe possibly other nearby galaxies.
I have dabbled a little bit in the Milky Way, yes, but largely I've focused on M31. But my PhD students worked on the Hercules dwarf galaxy, which is this interesting dwarf galaxy around the Milky Way, which appears to be much more elongated than most Milky Way dwarf galaxies. So there's a long-standing argument as to whether or not it's a dwarf galaxy that's in the process of being pulled apart. So then that's why it's kind of longer on the sky. And so she did a study to see how likely that was by comparing it to some models of what you would expect if it was being pulled apart. So we worked on that for a little bit. And then I've been involved in some Milky Way stuff as a co-author, but at a bit of a lower level. There's Triangulum 2 as well, which is a cool little dwarf galaxy that I worked on with Nicolas Martin. But yeah, just a few things in the Milky Way. And then also the Tucana dwarf galaxy, which is an isolated dwarf galaxy, which seems to be quite dense in terms of its dark matter content. So that one's a bit of higher mass than we would expect. And then I've just recently got involved in some imaging surveys where we're searching for faint dwarf galaxies around dwarf galaxies that are sort of more isolated and further away from the Milky Way, as another way of trying to learn about how these faint systems form and the different sort of physics that governs how they evolve.
I suppose it makes sense that you'd have co-orbiting dwarfs, but I just never heard of an example before. I'm not very cosmopolitan in my outlook. There really are known examples of dwarfs going around. Okay, all right. My world is enlarged, but that's what these shows are for.
So one good example is it's a sort of a higher mass dwarf, but the Large Magellanic Cloud has a number of dwarf galaxies now that we know orbit it. So SMC is one, they're a little bound pair, but also it has a number of very faint dwarf galaxies that we think now fell in with the Large Magellanic Cloud, so that that's like a bunch of dwarfs orbiting a dwarf. But then there's also some other examples. I think that I worked on a paper with Mike Rich on NGC 4449, which is a star bursting dwarf galaxy. And in its outskirts is like another smaller dwarf that's being sort of pulled apart as it orbits around. So that was a nice little dwarf orbiting a dwarf. And it was found actually at the same time by 2 different groups. So that was really cool as well.
Yeah, I'm on that Nature paper with you.
Yes, there you go.
That's one of the work I still dabble in now and then. So I was involved in that study. And indeed, we were some of the first folks to find a dwarf galaxy around another little dwarf, and it made it into Nature, which was great fun. And I think that is the most recent paper we were on together. That was in 2012. So
Yeah,
good times.
yeah.
So thank you for bringing that up. I didn't have to. I was going to. You and Michelle brought it up on your own. So how exciting. Gosh, what do you have that's your most current exciting target to go observe? Now, don't give away any research, of course, secrets you have, but if you have telescope time coming up, do you have any observing plans that you're excited?
No, I mean, we do have something exciting that's coming out soon, but I don't think I can talk about it yet.
Well, maybe you'll have to
You
come
could
back.
release a trailer, though.
Well, maybe
like
I will.
a teaser trailer.
Yeah.
But yeah, there's a cool little thing. I've been working with David Martinez Delgado on a really exciting project, actually. So that's coming out soon. And it's actually been mostly my PhD students that have been working on it, and which is nice as well. But I've been helping, as a good supervisor does. So that's a really exciting thing that's, in my opinion, that's coming out quite soon that I can't tell you about. And otherwise, one of my PhD students, Norshin Karim, is working on a survey of the halos of some isolated dwarf galaxies to look for these dwarfs of dwarfs, but also any evidence that they have maybe some stream features in their outskirts. And we're quite excited about a couple of things that we're seeing there, but we have to do a bit more statistics to see if they're actually real or if we're just squinting at blobs, which is unfortunately a lot of what I do these days. But yeah, so there's some very exciting work on trying to see how common dwarfs around dwarfs are. And we also think they might be interesting if you find them, because they'll be very faint systems that live around reasonably low mass galaxies. So they may have very different properties from the dwarf galaxies we see orbiting the Milky Way and Andromeda, just because they're living in a much less hostile environment. And much of what we know about very faint galaxies, we've learned from our immediate surroundings. So if we can find them in different environments, that's a really exciting thing in terms of learning more about these really interesting systems.
When you describe the environment as hostile, do you mean hostile to it continuing as one large blob? Gravitationally hostile, I presume. Okay.
Exactly, yeah.
You never know what's going on out there, really.
Yeah, I mean, who knows? But yeah, I think if you're living in the halo of the Milky Way and you get too close as a little dwarf galaxy, it can be quite bad for your continued survival. I mean, we see this with the Sagittarius dwarf galaxy. I mean, that was quite a big galaxy, and it's not faring so well these days.
No,
not at all.
Very sad.
Yeah. Now, a question that I got asked more when I went observing was, what was the weirdest thing that ever happened observing to me? Now, they always wanted tales of UFOs and aliens, and I had to tell them, no, actually, astronomers generally don't see UFOs and aliens. Maybe it's that we're familiar of what things are up in the night sky and know what to expect and can explain away much of what people think might be there. However, have you ever seen anything weird or had anything fun happen while observing, something unexpected?
So I've not seen anything weird, but I did have an observing trip a few years ago now with Nicolas Martin, and we'd gone to observe some Andromeda dwarf galaxies and streams at Keck. And when you go to use Keck, you don't actually go all the way up the mountain. You just go to Waimea and you remotely observe from the bottom of the mountain, which is quite nice because you don't get any of the altitude effects. Right. And there's a bunch of restaurants next door, so you can have a nice dinner before you start. It's all very civilized. But this time when we went on this trip, it was kind of a case, we were doing half nights. So we were doing the second half of 2 nights. And the first half was being observed by another group. They were working on something entirely different to what we were doing. And so we arrived on the first day. We decided we'd go for a little drive around the island. And we went on this drive, and almost immediately we were on a road cutting across the island. And we saw this truck coming towards us with like a big bird cage on the back of it. It was kind of teetering around, and it just fell directly in front of our car and then bounced out of our path. And we were like, oh, close call. That's a bit strange. Carried on with our drive, and we got round to Hilo. And suddenly the rain came in, and it was really quite intense. And the roads were getting kind of slick, but then we got back to Waimea. And as we did, all the TVs turned on to warn about flash flooding where we'd just driven. So we're like, oh, that's another bullet dodge. That's pretty good. And then we went to the observing room at about 2 o'clock to just check the setup and everything. And we were told that the person who was observing ahead of us had been involved in a car crash. and they weren't sure if he'd be back in time to observe, and they weren't sure if they could set up a remote connection for his team. So would we be able to do the observations if they couldn't do it? And we were like, I don't know. But luckily he showed up. He wasn't too injured from his car crash. He did his own observations. But then we had like an amazing clear night. We had perfect like conditions. It was great. We went to bed, and the next morning we got up, and there was like I don't know, half the island wide power cut. So there's no power anywhere. And we were told by the astronomers, like, if this continues, we're going to have to drive you up the mountain at 10 p.m. for you to do your observations, because there's just no way you can do it from here. So we had to like get up, like, so we'd gone to bed obviously, like in the morning, and then we had to get up at 10 and just go and see what was the deal. And they said, no, we could stay. Like, it seemed like the power was going to be okay. And then we did our observations there. Again, like perfect conditions, despite the weather being pretty terrible just before we started. So again, another perfect night. And then we were about to go home a couple of days after that, and this huge storm system was going to come in. Like, it was the biggest storm system that was going to hit the island for like years. And we were getting all of these hurricane alerts as we drove to the airport, and like people were trying to buy our tickets to get off the island. And so we managed to get off the island. And then when we landed in Seattle for our like change, there was also all these forest fires. And so we got off and everyone was wearing smog masks. And it's probably the most eventful trip I've ever had, where we had 100% success getting our observations at the same time. So just like a really wild ride of near chaos.
I have no idea how dangerous astronomy was. This is reading much more like Indiana Jones hacking his way through the jungles to get to the observatory.
Exactly.
There was a period of time where astronomy was one of the most dangerous professions on Earth. And it was because there were very few astronomers, and things like they would get in car wrecks driving up the mountain, fall off the mountain going up, or coming down in the morning, generally when you're tired, not so much going up. Or, you know, domes that rotate past things and people, anyway, horror stories. Very awful things have happened, but I'm glad you survived that night of observing, and I really appreciate you coming and sharing all these wonderful observing stories and the story behind that promo you made. We're going to have you back sometime when we're live again. Maybe you'll still be in England. We might do it remote, but we have no audience here to ask any questions, and normally they're pretty good and would pepper you with a few. So we'll bring you on back next time we're doing the show live, and next time you have a Keck run and a paper published to tell us all about, but we will expect a trailer. So just
yeah, for everything. You've raised the bar. You really have. And maybe action figures too. Yeah, we want a full campaign for this.
And everyone will know which one Andromeda 21 is. It'll be the one with the cool action figure. Yeah.
Absolutely. Well, thank you for joining us for tonight's All Space Considered. We really enjoyed our conversation with Dr. Michelle Collins, and all of the topics. Feel free to tweet at us, join our social media, join the Griffith Observatory Foundation if you've enjoyed the program. There's information down below in the description. All those links are there for you. But also, if you've stayed with us this long and you've enjoyed what you've seen, we have a little more of a dive into the sonification like we promised you. So enjoy hearing and seeing these astronomical images, and we'll see all of you next month on the first Friday, live remotely from Griffith Observatory.